Where is Swapan? Swapan Ray?
Okay, I think we will begin.
Yeah.
Professor Mishra? Yeah.
Yeah, he's not part of this panel, so
Okay.
I'm sure he's logged in, but only those who are speaking today would be in.
Okay. Good evening to all those who have logged in from India. Good afternoon to those in Europe, and very early good morning, I think, to those waking up and joining us from North America. My name is Ashok Kamath, and I am the secretary of the IIT Alumni Centre in Bengaluru, IIT ACB for short. And on behalf of IIT ACB, it is my privilege to welcome you to the Foundation Day program of the Polymer Processing Academy and to the workshop on polymer processing and emerging technologies. IIT ACB, an entity that was formed by alumni of all the IITs living in the Bangalore area, has the IITs as their partners. Our goal is to bring the academic community from the IITs and elsewhere and industry together so that collectively we can create wealth and wellness to all in society. The unfortunate pandemic created an opportunity for us. Workshops have always been an integral part of the IIT ACB efforts. And when the pandemic came about, we had an opportunity to take this to a different level, and we went using the webinar route. And for every single week since April 18th, 2020, we have been hosting a webinar on every Saturday. And over 20,000 people have watched this live or the recorded versions on YouTube. So the natural progression for us was to move workshops to a webinar mode. It might not be out of place for me to mention that our 11th webinar was delivered by Professor Mishra, and the topic was polymers. So Professor Mishra had spoken about this. So having said that, we moved all the webinars and we are now moving workshops to the webinar mode, and we are delighted to partner with the PPA in making this happen. We wish all the participants very successful 4 days of deliberations, and for you to enjoy the benefits of being at your home and enjoying the benefit of capabilities of all the stalwarts that we have today and over the next 3 days. Thank you and have a good time. I hand it over now to Professor Mangala Joshi for her to introduce the next speaker.
Yes. So thank you, Dr. Kamath, for introducing us to this conference, plus the Foundation Day program. So I will now invite Professor Ashok Mishra, the president of PPA, to give the presidential address. Professor Mishra needs no introduction to the polymer community, but I'll just give a brief about him for the people. So Professor Ashok Mishra is currently NASI, National Academy of Sciences India Distinguished Professor at the Indian Institute of Science, Bangalore. Earlier, he was Director IIT Bombay, Chairman India Intellectual Ventures and at IIT Delhi. He is a director on the boards of Jubilant Life Sciences, Jubilant Pharma, Kirloskar Electric Company, and Higher Education Financing Agency. Earlier, he was on the boards of Reliance Industries, NTPC, and RCF. He has held several responsibilities with MHRD, including chairman of the Standing Committee of the IIT Council. He is a fellow of National Academy of Sciences India and was its president from 2006 to 2008, a fellow of the Indian National Academy of Engineering, founder president of the Polymer Processing Academy, which is organizing this event, and also member of several professional societies and the founder president of IIT Alumni Centre at Bengaluru. So with this small introduction, I request Professor Mishra to deliver his presidential address. Professor Mishra, please.
Yeah. So good evening to all my friends in India. Good afternoon to those who are attending from Europe, and a very good early morning to those who may be in the States. I don't know how many have joined so far and so on. First of all, it's my pleasure to welcome Professor M.M. Sharma, Professor Brigitte Foyt, and Professor David Hoagland, who hopefully is waking up and will join later, and all the participants who are attending this 4-day event on behalf of the Polymer Processing Academy. Just to give you a brief, we formed the Polymer Processing Academy in 2011 to be a nodal agency, nodal society for interaction between the polymer fraternity in the global sense, and also in areas of with participants from the academics, the research institutions, and the industry. It has been very successful, this interaction, and I'm proud to say that we have a participation from all these 3 sectors, including several from abroad. We have had several conferences. We have been very active and organized several conferences, several talks we have held. We have supported a bunch of colleges who are concentrating on polymer science and engineering. And we inaugurated our society with a launch function at Mumbai in 2011 with the first Foundation Day lecture in March. Since then, we have been a regular in holding a Foundation Day lecture every year with a person of eminence in mostly in the area of polymers, but sometimes in cross-disciplinary areas. This year being a little special, it's 100 years of polymers since Hermann Staudinger talked about long-chain molecules and introduced them to the world, to scientists like at that time. He later on went on to win the Nobel Prize in 1953. So in his honor and in polymers completing 100 years, we decided to call this Foundation Day theme as 100 years of polymers and beyond. We are delighted that Professor Brigitte Foyt and Professor David Hoagland will be delivering these lectures. This is the first time, and because it's a special occasion, we have 2 prominent, eminent speakers at the Foundation Day. Normally, as I mentioned, we have only 1. This will be followed by a 3-day web-based conference oblique workshop in the area of polymers. We were actually planning to hold the regional meeting of the Polymer Processing Society on these exact dates. And because of the pandemic, everything went haywire and in-person meetings were not possible. So we took that opportunity to hold a 3-day conference on polymer processing and the new innovation that are taking place in this area. So welcome to all of you. We look forward to your active participation. I must also mention that this is the first time we are doing a 4-day event actually on the web, and hopefully with our experience through holding webinars, it should go all right. But normally those are 1-day events or half-day events. Let's hope that everything works by clockwork. Now it's my pleasure to welcome again Professor M.M. Sharma, who very readily agreed to give the inaugural address to this 4-day event, starting from the Foundation Day today. It's absolute pleasure for me to introduce Professor M.M. Sharma. Professor Manmohan Sharma MM as he's called for short, is an outstanding chemical engineer who has made enormous contribution to the chemical industry in India and in the global world. Further, he has contributed extensively to the growth of science and technology and engineering in India with active involvement in framing the policies with the government of India. He was appointed professor at the age of 27, very young age of 27, at the Indian, at that time called the UDCT, University Department of Chemical Technology, now called the Institute of Chemical Technology in Mumbai. I must mention, I was a student at IIT Kanpur, and we had a conference on chemical engineering, and we were so excited to see and meet this young professor from Bombay who came and gave an outstanding talk. Of course, he will not remember me from that time, but I've had extensive interactions with him later on, especially when he was on the board of IIT Bombay, board of directors of IIT Bombay, and I was the director. At that time, I saw his passion for research, a strong advocate of research in the country in mainly the engineering colleges. That was his forte in science and engineering. And he was very, very supportive of the programs that we initiated. And I would like to put on record my thanks to the support I received from him personally and for the institute. Professor Sharma, in that sense, doesn't need much introduction. Everybody knows him very, very well, but I will just be very brief because I'd rather hear him than have a lengthy introduction. Professor Sharma was the first Indian engineer to be elected as a Fellow of the Royal Society, UK, an honor for the country. Later, he was elected as an honorary Fellow by the Royal Academy of Engineering, again in UK, and a Foreign Associate of the US National Academy of Engineering. In India, he is a Fellow of all the three science academies. He is a recipient of many, many prestigious awards and honors that include the Liverpool Medal, the S.S. Bhatnagar Prize in Engineering Sciences, the Vishwakarma Medal of INSA, the J.M. Modi Award, the Meghnad Saha Medal, and many, many more. I'll just leave it at that. Mainly because of his outstanding work in the area of chemical engineering. For his several academic contributions, he has been honored by a number of universities and the Indian Institutes of Technology with honorary degrees. Professor Sharma was conferred with the Padma Bhushan in 1987 and the Padma Vibhushan in 2001 by the President of India for his enormous contributions to science, engineering, and technology in the country. With these, I hand over the proceedings to Professor M.M. Sharma to give his inaugural address. Professor Sharma.
Thank you, Professor Ashok Mishra. It's a pleasure to be with you and your colleague Arup Ghosh and others. It's very remarkable that you organize this specific occasion of a centenary of a truly outstanding piece of work by Stauringer. But let us not forget 1909 work of Bakelite. That was one of the, and nearer home, let us not forget that right from the time of Mahabharat, we knew they were shellac. In fact, that was the first important polymer, so much so that British organized Indian Lag Research Institute in India because gramophone records, polish, name it, everything was made, and it's an excretion product of insects grown extensively in what is now Jharkhand. But this was then copied by other countries also. Now, these 100 years have been really spectacular. Why? First of all, the science has progressed, the polymer science has progressed in a dramatic way. The manner in which we can manipulate molecules, carry out polymerization stereospecific polymerization, even now heading towards chiral polymers. It is so pleasing. So has been the polymer technology, polymer engineering. I like to just give you two examples to show the kind of development that has taken place with very heavy inputs of chemical engineering. And that was in 70s when fluidized bed, what has happened? I'm not on the screen. Am I audible?
Yes, you're fine. Please go ahead.
I'm not. I'm visible now?
Yes,
Yes.
yes,
Okay.
very much.
Well, with heavy inputs of chemical engineering in early 70s, when fluidized bed polymerization came for a polyethylene as well as polypropylene and linear low density polyethylene came. Those of you who go back to the original literature in late 30s and early 40s, particularly during Second War, you will find entire literature on fluidized bed had no mention that fluidized bed can be used for polymerization. These reactors were so good that 1,000 tons per day could be processed. Similarly, in polymer processing, there have been spectacular developments. So all along, and then of course, the science was so strong, like Staudinger, at least 6 Nobel Prizes have come. But what is interesting is, in the history, that number of important products were serendipitous. It started with LDP in ICI. HDP is also believed to be serendipitous. Cellulose nitrate was serendipitous. Teflon was serendipitous. But none of these serendipitous things occurred to people who are not highly talented and initiated in this whole business. It's a little known fact that LDP gave British an edge just during Second War, because that was the only material that could be used for insulating radar. And Germans didn't have LDP, so they could not have radar. You know, this only shows that polymers have a bizarre range of properties. They can be insulating, they could be conducting, and you know what kudos came when conducting polymers came. I am very excited when you hear about polymers performing all around. Imagine packaging without polymers. Every day, when we begin our day and close our day, we are dealing with polymers, whether it's toothbrush or whether it is a brush. While I mentioned about serendipitous discovery, I want to stress very heavily that the first and the foremost example in the history of chemical industry was the discovery-driven product nylon 6,6 by Carruthers in DuPont. It's an extraordinary example when Carruthers was hired by DuPont and given a carte blanche to do something original. He came out with the, the rubber earlier, but that wasn't nitrile rubber, that wasn't chloropene, polychloropene rubber, but that wasn't that great an achievement as nylon 6,6. And the same nylon has seen market-driven growth because aromatic polyamides, Kevlar and all, again from DuPont. So you can see for yourself that polymers saw this spectacular development entirely discovery-driven. We are still finding newer uses for nylon, although for apparels, nylon gave way to polyester, which came around the contemporary period, developed both simultaneously by ICI and DuPont. Imagine the fate of not so well people in India, ladies from economically weak background. What an impact polyester saris have made. Every person you see in India today would be wearing a very good sari and is entirely due to availability of polyester. And this same polyester has this extraordinary range of properties, from polymer, film, you can make fiber, staple, filament. PET bottles again have a very interesting story of development to show persistence. Mr. Wyeth in DuPont had 10,000 failures in developing the recipe to make PET bottles. And you know, today, something like 60 billion bottles of PET are made. And PET can be completely recycled. I understand, I think Sopan Ray will probably endorse that something like 80% of PET is being recycled in India into some value-added products. Now, polymers show all kinds of extraordinary properties. Now, we had thermosets also, which brought about so many changes. But reinforced plastic allowed Dreamliner to be light. So you could make originally the military aircrafts, which made use of reinforced polymers so that they could be lightweight. So you see the manner in which polymers are being used. I think it's very difficult to make a living today without making use of polymers. And of course, people are talking about circular economy. Technology will come up because after all, what is polyethylene? They're glorified wax. You will be able to crack it to olefins. You will be able to crack it to the oil, which can be recycled into naphtha crackers or gas oil crackers. And large size pilot plants already exist. I have every reason to believe that the circular economy will be practiced, which is one of the severe criticism that, you know, you are not able to reuse. Polyester is a very good example. But let me also give you an example which is not quoted very much, and that is PMMA, polymethyl methacrylate. Polymethyl methacrylate is very easy to recycle because you can get back the monomer from PMMA and you get very good quality polymerized material from the recovered material. Now, I did talk about so many developments that took place. Well, polycarbonate came, but before that, transparent plastic came in the form of PMMA, but it did not have very high impact strength. But polycarbonate had very high impact strength. So for security purposes, many places where for security people were using glass, they moved on to polycarbonate. Polycarbonate was for a while a variety which could even be retorted. But lately there has been some criticism of polycarbonate because of bisphenol A. But there are many polycarbonates which are not made from bisphenol A, but some very sophisticated polycarbonate for electronic purposes are made from bisphenol, which is made from trimethyl cyclohexanone. So, you know, we have problems, but in the present context of COVID, about which references were made both by the IIT Mr. Kamath and by Ashok, COVID has really shown the remarkable strength of polymers. Imagine how you will deal with syringes if you were not using polymer. Imagine all the safety PPA, whatever they call, they are all polymeric materials. Polypropylene saw a spectacular use in this context. So whenever we get into problems, we look at, well, let me know when we talk about what impact it has made to everyday life, to the society. So I'd like to pick up 2-3 examples. First, how the quality of life has been affected from the moment the child is born to a girl which grows up, diaper and sanitary towel. Imagine if these were not available, what would have been the sanitary conditions? People tend to forget that polymers have made such an extraordinary impact in terms of quality of life. But I also want to show how the quality water, which is essential for life, and wherever there is water shortage, but you are on the coast or your brackish water is available, how reverse osmosis membranes, and they started with flat sheets and then you had hollow fibers. The hollow fibers came because there was expertise of polyester and nylon being converted into fiber, and you see the whole varieties of polymers which are used to make membranes. And desalination is in the vocabulary of the most common person in India or elsewhere in the world, because everybody uses the word RO water. They may not know what RO stands for, but RO water, even Panipuri wala in India says his water is RO water. Now imagine, can you have RO water without polymer? This only shows you that polymers conserve energy. Very often there is a reference made to paper. But what people are forgetting is paper means for population, large population in India, where are forests? For us to conserve forests, unlike what happens in Scandinavia or Canada, we don't have pulp in the quantities that want. The amount of water that is required in making paper, and on top of it, the range of chemicals that we require to make paper. So paper is not all that benign as people tend to tell you. Similarly, very often they make a reference to glass, forgetting that weight is very high, and if a glass bottle falls, you may hurt your feet or your hand if it cracked in your hand, whereas nothing will happen if you had a PET bottle. So polymers also epitomize safety. Now I can go on and tell you how it has made such a fantastic effect. Engineering plastics now, and we also look at adhesives. What are the adhesives that we knew in our childhood? In my childhood, I knew that I could make starch and then make some envelopes, and everybody knew that termites would attack them. Whereas now, imagine how the whole world of adhesives has changed just because of polyvinyl acetate. And Fevicol is in fact, it has gone into cinema songs also in India, because, something sticks, they said, Fevicol light. So, some of these items have gone into the vocabulary of every individual in India. They will always say, if adhesive, it must be something like the product I refer to. But there are engineering adhesives. How these engineering adhesives, dissimilar materials you can join. It was unthinkable earlier, but for polymers, it has been made possible. I can go on and on, but I also want to say that there hasn't been really a totally new polymer for a long time. But existing polymers have been taken to higher and higher levels. Look at even polyethylene film, it becomes thinner and thinner and stronger, or BOPP or other polyester film or polycarbonate film. But where is the new polymer? Some of you may remember when Shell had supposedly a breakthrough that they would polymerize propylene with carbon monoxide to make nylon-like material, and a 30,000 ton plant was put up. It turned out to be a flop. Just as you would also remember synthetic leather Corfram from DuPont, because it was not marketed properly, it didn't turn out to be successful. But it was a very good development based on urethane. So everything is not all that great. But I'm looking forward. We are saying, as your title says, I do hope some new varieties of functional polymers will come. Fluoroelastomers, fluoropolymers made a big difference. Nothing is more slippery than Teflon. So politicians always say this. They will say this politician is Teflon-like because he's very, very slippery. Finally, I want to stress that we have to learn a lot from nature. Nature is able to do everything under ambient conditions. I'm not referring to cellulose, but look at silk, a protein base. A fiber comes out. Can we imagine a situation where we'll have monomer directly going to a fiber? Cellulose was used extensively. I'm not talking about just regenerated cellulose in terms of viscose or cellulose acetate, but cellulose acetate was a wonder material. It was plastic, it was film, it was fiber. Cellulose acetate fiber still is considered very good for dress material for women. Would we see renaissance because this is all renewable? Major part of the weight is renewable because polylactic acid hasn't stayed with the promise that was projected at that time that it will displace polyester. Similarly, The hydroxybutyric part, which ICI tried to introduce, also did not go to the kind of success that anybody was imagining. So nature can make natural rubber at ambient conditions, terpene resins at ambient conditions. Do we have any parallel to that? Imagine our making synthetic natural rubber. First, isoprene synthesis itself is quite involved, and so is the polymerization. But then there have been success also that how we have bridged the gulf between thermoplastic and elastomers by having TP, thermoplastic elastomers. It's a pity that in India we still don't have thermoplastic elastomers. And EPDM, which we tried to launch where I was involved, unfortunately, there is no production now of EPDM in India. I hope before long we don't go so much for vulcanization of rubber, that we go for thermoplastic elastomer. And one big target should be all these shoes for children going to school, canvas shoes. Upper can be in recycled polyester, and it may be injection molded, so there's no wastage, no nasty chemicals being used. Once again, I want to compliment Ashok Mishra and company, Arup, and all those who have participated in this. You have done an extraordinary job of remembering somebody who made such seminal contribution. And the whole area of polymers is so exciting that this excitement has no limits. Thank you very much. I've stuck to my 20 minutes.
Yes.
Yeah. So
Thank you so much for a lovely talk. Over to Mangala.
Yeah. So thank you, Professor Sharma, for your exemplary lecture, which really took us through the history of polymers, where you started from even before Staudinger, the bakelite, and then how Staudinger, first time published an article on polymerization, that polymers are long chain molecules built up of covalently linked building blocks. You took us through the journey of polymers from the earlier polymers, and then the synthetic the rubbers, and then through the bakelite, PET. You told about PET, and then the coming of reinforced plastics. In fact, I did my PhD in reinforced glass reinforced plastics way back in 90s, and then polycarbonate coming over as a glass replacement for glass, polyethylene. And then the most important is that you stressed upon the need that the life cannot be thought about without polymers at the current stage. There are challenges, but as you rightly said, new polymers are yet to come. And you briefly talked about how nature synthesizes the polymer using the self-assembly process. We call it the bottom-up approach of nanotechnology. And I do teach that concept in the class, and I say that how nature makes such high molecular weight cellulose in a cotton fiber, and how we make in the lab. So there is a difference there. And then finally you said that COVID-19 is one, the pandemic has brought to the fore again the importance of polymers, because there was some criticism about polymers because of its non-biodegradable nature and the recycling effect. But as you rightly said, COVID-19 has brought forward again the importance of polymers in the human life. So with this, sir, I thank you so much for taking us through this journey of polymers. And we thank you from our heart for taking out your time and, giving us such a lovely talk. Thank you, sir, once again.
Thank you.
And now we will move on to the second lecture, which will be given by Professor Brigitte Voigt from Germany. I'll just give a brief profile of us. Professor Voigt received her PhD in macromolecular chemistry in 1990 from University of Beirut, Germany. After postdoctoral work in 1991 and 92 at Eastman Kodak in Rochester, USA, she joined Techni University of Munich And after habilitation in 1996, she was appointed in 1997 full professor for organic chemistry of polymers at Technical University Dresden, as well as head of the Institute of Macromolecular Chemistry at Leibniz Institute of Polymer Research, IPF Dresden, where she is since 2002. She is also the scientific director, and her scientific interests are in the area of functional polymer architecture. So, with this brief introduction, I request Professor Foyt to take over and give your lecture. All the participants are looking forward to it. So, on to Professor.
Yeah. Thank you very much. I hope you can hear me and understand me well. It's a real pleasure for me and also an honor to be able today to talk to you and to be invited by the organizer to talk about 100 years of polymers and celebrate with this topic your Foundation Day. As you might be aware, Hermann Staudinger, who was just introduced so very nicely by Professor Sharma, introduced the concept of polymers 100 years ago. And of course, since his main activity was located in Germany, it's especially for the polymer community in Germany, a really big event to celebrate those 100 years of polymers in 2020. Unfortunately, as we are all aware, the celebrations are a bit different as planned, but we also had a one-day celebration day for, in September honoring Hermann Staudinger. Now, I'm a polymer chemist, and therefore I'm very much grateful to Professor Sharma that he gave such a beautiful introduction on the history of polymers, but also pointing out the importance of polymers for our society and the huge advancement we have made with the concept of polymers and the materials which came out from that and which made our life much better and safer as it had been before. But he also pointed out, of course, there is much to do and also much to consider. And we also have to face the problems which come with polymers. Today, I will talk about modern polymer synthesis towards advanced functional material. And it was already pointed out, yes, there are no real new polymers around. That is in principle true when you look for the large-scale polymers which we use and which are used in building and in packaging. However, there's a lot of progress also in polymer synthesis and making materials better, but also making new functions into polymers. And I would like to introduce to you. Now, as already mentioned, and I have it now easy because it was introduced already, 100 years ago, Professor Staudinger pointed out to the community that the concept of large macromolecular chains. So he was clearly pointing out that in polymers or plastics, there are covalent bonding between the different building blocks. And this concept of covalent bonding was very much important because that allowed to think about the synthetic methods to make polymers and also to make tailor-made polymers. And that was the starting point of polymer science in general. Here you see Staudinger with a model of a polymer chain. And you see also Staudinger when he was awarded the Nobel Prize in 1953. The main discovery was actually done by Staudinger in Zurich and in Freiburg, where he started his career and developed and disputed a lot actually with his colleagues because it was a very new concept and the colleagues were not agreeing with him that the such large macromolecules really exist. They were in the beginning claiming it's more associates. Actually, now it's coming back to associates in science again. Also, the history was already pointed out to you that even before Staudinger, of course, there had been polymers and plastics around. It was pointed out very nicely, bakelite, for example, but also some other material like polyisoprene, polyacrylic esters. And it was nicely shown and pointed out as a huge development in the last century, more or less until about 1957, 1960, all the major polymers had been developed. And it's true, since then, it's maybe difficult to see the real new polymers around, but from the synthetic point of view, and I'm a polymer synthesist, actually since about 1970, 1975, there was the beginning of the macromolecular engineering, meaning to make very defined macromolecules. So again, coming back to the concept of a macromolecule, a chain molecule, which you can design monomer by monomer if possible, and also in the architecture. So that was the starting point of anionic polymerization, block copolymerization, star polymers. Then in the middle of the 80s, there was a concept of dendritic polymers. And since the middle of the 19th, there are controlled polymerization techniques like controlled radical polymerization, ring opening metathesis polymerization. So various types to control the materials very well. Today, for a polymer chemist, there's a lot of things to do. You use today also different chemistry to modify your polymers or to use your polymers. You have the term of click chemistry, you will see a bit in my lecture, but you can also make precision polymers. You have the concept of dynamic covalent bonding, where you can make vitrimers and self-healing polymers. Self-assembly has been mentioned, and yes, it's a starting point of nanostructure. And there is also the possibility now to have controlled polycondensation, which is similar to a controlled chain growth. And today I will actually show you examples from the field of self-assembly for functional materials for biomedical and biotechnology application. And also I would like to show you something about the controlled polycondensates, which are especially interesting to make functional polymers for optoelectronic applications. The Nobel Prizes have been already pointed out. There have been several ones, of course, for Staudinger, for Ziegler-Natta, for Flori, and also in 2000 for the conducting polymers. Okay, so field of smart nanocapsules, and I hope you see already here, they are really beautiful. So nanocapsules are a compartment with the membrane, which is usually filled, for example, with water, but you can also fill other things in. You see the membrane very nicely. It can be quite tight, and you can control also the size between 50 to 100 nanometer to also micrometer size. We started in my group to get into it by making polymersomes. Polymersomes are a synthetic analogy of liposomes. Liposomes, you know very well, they are essential in our living organisms and in ourselves. They are usually prepared by phospholipids, surfactants, which assembly into so-called vesicles. And you can do the same thing by using block copolymers, having a self-assembly procedure and make a vesicle. Those vesicles are highly interested, and there had been studies since about 20 years in various fields as nanoreactors on surfaces and as complex matter, which is going into synthetic biology. We addressed specifically in my lab material which is pH sensitive. So you have a pH sensitive block copolymer, which is under certain conditions water soluble, and when you change pH, it becomes amphiphilic. And as soon as it's amphiphilic, it can, under the right conditions, assemble to a vesicle. And we wanted to come from a vesicle which assembles and deassembles into a more stable structure, a nanocapsule, which can actually reversible swell and deswell. And for that, we introduced UV irradiation to actually cross-link the membrane after the assembly. And if this is working well, and it worked well in our case, you can actually avoid disassembly, and you can swell and deswell the vesicle, the nanocapsule, and get an on and off state of that material where the membrane is leaky or the membrane is closed, and that worked very well. Okay, chemistry behind is a chondroid radical polymerization. We used ATRP in that case to make a block copolymer having a polar PEC chain and a less polar middle chain, which contains a pH-sensitive unit, in that case, this tertiary amine. And it contains a cross-linking unit, as you see a unit here, which can used to be photocross-linkable. The material can assemble depending on the pH. So as soon as when it's protonated, it's soluble. When you deprotonate it, it assembles. And of course, as soon as that goes back and forth. When you do it like we shown here, we make the assembly, we cross-link in the assembled state by UV. Then you finally get a cross-link membrane and you can swell the membrane. It's like a hydrogel, but it cannot disintegrate. And we proved this on various cycles. So you can see here that the material works well. You can switch on and off from leaky and swollen to collapsed, and you can do it many cycles. The material can be quite stable when you do the right cross-linking. And you can also see that the membrane changes in thickness. It becomes very fuzzy when it's swollen and thicker, and it becomes denser when it's unswollen. So I hope everything works so fine. Yep. Okay. Once you have the assembly under control, you can start to think what to do with such nanocapsules. One possibility is you use them in drug delivery, for example. So you use them just as a container. And we started relatively early on to study that field. And for that, of course, interesting is a targeted drug delivery. So we started to introduce a folate unit. A folate unit can be used for cell targeting. And we introduced, in addition, also a marker which allows us to follow our nanomaterial in cells, for example. So the assembly process works also with functional material. So when we had the functionality at the chain end, it worked well. We actually made the PEC a bit longer so that the functional groups, especially the targeting groups, really stick out. So they are very much available for targeting. The assembly works very well, no matter if we have the folate material onto it or not. You see the capsules, they are robust, and you can do also a switching several times, no problem. Once we looked for cellular uptake, we could recognize that the cellular uptake worked well, and we got a significant higher cellular uptake in the case when we added our targeting unit. So we got a 4 times enhanced uptake, so 400% enhanced uptake in the cells which had been the respective cancer cells which had been used in that study. So the concept worked well. And we could also finally prove that we can use the material not only as container, which allows the specific targeting, but we could also use them as drug delivery system. So we used doxorubicin, which was loaded in our containers. And when we had good targeting efficiency, we got a good cell death of our of the respective cancer cells. And that was important that actually the cancer cells showed a significant cell death up to 45%, which was similar to the 40% of the free doxorubicin. But when you use free doxorubicin, also the healthy HEC cells, for example, died. However, they are quite protected in the case when the targeting works, because now mainly the drug, the doxorubicin, was delivered to the cancer cells and not to the healthy cells. And that is the advantage of targeting in cancer therapeutic approaches, that you actually avoid that the healthy cells are also damaged in this treatment. Okay, so you hope to have seen that it works already well, for example, with a specific functionalization. This only shows you that we can do actually a lot of functionalization. Our cross-linked nanocapsules are really quite robust. You can introduce various types of functionality like A sites for click reactions. You can also use some photoprotecting groups. You can use targeting moieties. You can introduce host-guest interactions on the surface of such nanocapsules. And they really survive also treatments very well. And we have now established good routine work to even store our nanocapsules for a long time and reactivate them and even can ship them for several months, no problem. They are stable and reusable for various types of approaches. For example, we also put them onto surfaces by a non-covalent bonding, having cyclodextrin and adamantane and a nice host-guest bonding, so they can stick to the surface. We can do irradiation of photoprotecting group and then put some marker on it. It works well. You see here, when you have sufficient imaging with light of the right wavelengths, you see that actually those nanocapsules light up, and it works very well. Even in a so-called 2-photon absorption regimes, it works very well. Very nicely is also the use of such material as a nanoreactor. And you see here as a concept, you have the block copolymers. You have, for example, an enzyme. You make the assembly process under the right pH conditions. You isolate your polymersomes, now loaded with enzymes. You cross-link, and now the enzyme is nicely inside. You cleave everything, which is not encapsulated. We use a hollow fiber filtration method for that one. And then you have a nanoreactor with an enzyme encapsulated. And depending on the pH, you can also control the enzyme reaction. At lower pH and in the acidic regime, the substrate and the product can diffuse through the membrane. At the higher pH, the membrane is closed and no diffusion happens, and therefore there is no reaction. That works well. In a first example, we used myoglobin, which converts peroxides to colored product, which you can detect very nicely. And you see only at pH 6, you see a nice production of the colored product. You can do this also for various types of reaction. We made also cascade reactions using two enzymes, the glucose oxidase, which produces peroxide, and this peroxide has been then converted with myoglobin into the colored product. And we looked how we can do it with the different encapsulated enzymes. And I just want to show you that it works also well when you individually encapsulate the enzyme and allow a cascade reaction. And it actually has to do both. First, you have a diffusion into one nanoreactor, product is formed, product then diffuses in the other nanoreactor and produces the final product. And it works again very well, pH dependent. Now you will say, why is it important? Actually, there's a huge need for having active enzymes also for a longer time. And when you have the enzyme in such a controlled environment like a polymersome, the enzyme is, the activity of the enzyme can last much longer. And that's especially of importance for biotechnology, where you use enzymes for really technical production of products. So you can see here, when we have the enzyme in the polymersome, we can keep the activity for 10 days. It was studied here for 10 days. Whereas when you have it in the pure state, not encapsulated, after 4 days, there's nearly no more activity here existing. This is shown for quite some well-known enzymes. We are studying presently also much more complex enzymes, which are not for model reactions, but which are, for example, also used for the production of specific drugs, for example. So I hope I could convince you that's very nice. So you can make such a polymersome. The polymersomes we prepare are in the range of 100 to 150 nanometer in diameter. We can really use them for a lot of interesting reactions. That's a very recent publication where we used also a light-driven proton transfer. So by light, protons were created, and that allowed finally the transport into such polymersomes and also the activity of enzymes which had been encapsulated. But we wanted to go a step further. As mentioned in the beginning, polymersomes are mimicking liposomes, which are the typical vesicles also in organic living organisms. But of course, there is a much more complex feature there. When you talk about cellular mimics, then you have not only one compartment, you have many compartments in a larger compartments. Though our next aim was to go from the bio-nanoreactor to more synthetic biology and start to think about multi-compartment systems and interactions between the different compartments within a larger structure. So getting closer to a cellular-like structure and mimicking transport and reactions which are happening in a cell. So for that, we need a larger compartment. The polymersomes we prepare so far by the self-assembly process are limited in size. We can control it a bit by the molecular weight, but not so much. But we have another tool, which we are doing in cooperation with Professor Huang in China. And he is doing biohybrids between a protein and polynipam, which is a thermoresponsive polymer. And by that, you get those biohybrids and you can assemble them into giant vesicles. So those vesicles are in the range of micrometer, up to 20 micrometer even. And we were thinking, okay, we'd use those giant vesicles as the outer compartment, like the cell membrane, and put some interesting polymersomes inside to have a multi-compartment system. That worked, I can tell you. So we made different types of polymersomes and we loaded the different type of polymersomes with different enzymes and put everything into a membrane of our biohybrid structure. And in the next picture, you hopefully see it a bit. We imaged the different components. So we had polymersome A labeled with a dye and a polymersome B labeled with a different dye. And you can now see that both polymersomes are present. Then we have labeled our compartments, which are built by the biohybrids. And when you have the overlay, you see that really it was possible to fill the compartments with both polymersomes at the same time. And when you look here, you see that we can also see the activity of our encapsulated enzymes, which are encapsulated in the polymersome, and the polymersomes are encapsulated into the proteinosome. And you still see the activity. The activity is lower, only about 25% of the free enzyme, but it works well, and you can now have the engagement of different polymersomes within such a proteinosome. A different approach to make the larger capsules is shown here. That is a templating approach for making capsules. So the other one was self-assembly. Templating is a bit different. You start with a silica particle. This defines the final size. You can do grafting on it to make finally a stable polymersome, or in this case, a capsule. You have again to do cross-linking to be sure that the capsule is stable. After that, you can remove the core just by with ammonium fluoride, for example, and that gives you a capsule. The other approach we also used is, again, starting from a template, and on the template, you actually build up layer by layer a shell, and this shell you also cross-link. So that is the layer by layer approach, and finally, after cross-linking, you can also remove the the core and have the capsule open. So both were used. You see here some pictures. We used again controlled radical polymerization, so-called raft process. Did the cross-linking, removed the core, and you see beautiful capsules which resemble now in size the template which we used. And you can even make some more nice chemistry. For example, we introduced here disulfide units, which we then used for a disulfide cross-linking. And that is, of course, a cross-linking which is sensitive to redox reactions. And therefore, we can also disintegrate our membranes. Now, first you see nice capsules, beautiful capsules. They are very nice and stable. The swelling depends a bit on the cross-linking. So when you have a larger cross-linker, you get more swelling. And it depends on the pH, of course. And these capsules can be post-loaded. And that's something which is very interesting. The capsules are in the swollen state. They have large holes which allow material which is in the range of a couple nanometers, for example, an enzyme, up to 5-6 nanometers. They actually in the swollen states, they can move in. And when you then control pH relatively well, it sticks in also. So, and then you can use also those capsules nicely as reactors, having enzymes inside and having the control by pH between an open and an off state of the material. Okay, a couple more chemistry, because I wanted to show you also the techniques which have been developed in the last years for making very much controlled synthesis. You see here a variation of the ATRP. It's a so-called ZLRP. It's again a living radical polymerization. It allows you, and we developed a very nice scheme to also make block copolymers. And we made a nice development here that we got really very thick membranes by that grafting process of a terpolymer, for example. And that is also nicely controllable. It contains a pH sensitive as well as a temperature sensitive material. And you can control now the diffusion by both pH and by temperature. And that's shown here. We always show that the diffusion works and we can control it by encapsulating enzymes. The enzymes allow us to follow if it works or not and how is the pH dependency. And I hope you see that we have on the one hand pH dependency, shown here, but we also have the temperature dependency from the both components in the shell which we used for our capsules. One part still I wanted to show you here is a complex one. I showed you the layer by layer approach to make the capsules, and that is used to make a very interesting multi-component compartment. And I will not really show you how the chemistry works. It's quite complex, but in the final state, we were able to have lots of polymersomes in such a larger compartment. And the polymersomes had all been loaded with enzyme, and you can nicely show that those material actually work and interact. Also, when you have encapsulated several enzymes, you get also cascade reactions in such a large compartment. And we are quite proud about that possibility. And the student was really an excellent chemist to finally, and also innovative to come up with this idea. So I hope the first part of my lecture showed you already that the polymer synthesis inspired by Staudinger, who showed, okay, you can use chemistry and make defined bonding, is very nicely used also in functional polymers. And I showed you the modern topic of self-assembly to make nanocapsules, especially for biotechnology and for synthetic biology and biotechnology. The second part I wanted to briefly also touch is polymers designed for flexible and optoelectronics. I think that is another area which is presently very strongly developing, and addressing modern technology and also progress in modern technology, which is very important also for our future life. The point is here that, of course, we know microelectronics and we like all our computers and we need them very much in the present time. So information processing is very important, but as polymers having the possibility to use them in flexible electronics makes things cheaper. So you can produce them by a very different technique, just by typical printing techniques. It makes it cheaper and it makes it available for smart systems, for smart flexible systems. And a lot of applications are, on the one hand, again, in biotechnology, biomedicine, on the other hand, in more sensing material, in autonomous processes, in robotics, and also things where we need information processing directly on the spot, directly in the device, but reliable and relatively easy to produce to make it also available for a broad application. And I will show you a bit what is behind that. And again, chemistry, which is of course very important in that field. I mentioned already there had been a Nobel Prize also on the field on conducting polymers by awarded to Higa, McDiarmid, and Shirakawa. That was for the development of polyacetylene, and which is a conjugated and also conductive polymer after doping. And that's an important point. Usually when you make a polymer and it's conjugated, it might just be semiconductors. And that's actually what you need in organic electronics. You need a semiconductor, but the semiconductor should also be able to become conductive by doping. So that is, and of course, what we want to have is a low-cost roll-to-roll processing. So soluble materials, which you can have on flexible substrates. The synthesis usually done for such pi-conjugated polymers are step growth polymerizations, where you have an AA component or a BB component, which are coupled together by CC coupling. Much of it is Stille condensation or Suzuki polycondensation. You know, also nice name reactions like Kumada, Negishi, Sonogashira, Heck, and so forth. Also, materials are beautifully developed and work well. You need a catalyst, that's important, and it's a step growth material. And you might all remember there's chain growth and step growth, and in step growth there are often limitations. You need a very high conversion and very efficient reactions to finally come to a polymer. In the 2000, roughly by Yokosawa and McCullough, there was a new concept introduced that is chain growth condensation polymerization of AB monomers, which finally leads, for example, here to a polythiophene, which is by a product by CC coupling. But this procedure to make this polythiophene is actually following a chain growth. So you have a catalyst which is more or less sticking to the chain end, and this catalyst allows a more or less defined polymerization. And when you do it right, you can actually get a living type of polymerization where your monomer develops linearly, molecular weight develops linearly with the monomer conversion, and you get a nice small dispersity of the material. And you can control the end groups very well. You have a starting group, you have an end group. You can make block copolymers, for example. So that had been developed by us quite a bit in the field of functional polymers. For example, we made polythiophene, which we conjugated to DNA. And then you have, again, a hybrid material. And this hybrid material was used to decorate DNA origami with such conducting layers and stripes. So that is actually a DNA origami. You might know that you can assemble specific DNA strands into defined structures by designing the DNA. And when you have a DNA strand which is complementary to some of those DNA strands here, you get specific site-specific attachment of the hybrids we used here. And you can make oligomers, which are interesting for nanoelectronics. So you can make attachment points on such a molecule, which even can have additional donor acceptor moieties, and put them as single nano macromolecules here for making devices on a nanometer scale. That works also well. We developed it quite a bit for different types of materials, as shown here. This is an N-type polymer, so it's an N-type conjugated polymer, which is quite useful and has good performance, and it's very much liked. We developed this also for our specific chain growth condensation process, and developed a specific actually a mechanism which goes through a radical anion, but it works really well. So we can make material which follow also a controlled mechanism where we can control the molecular weight relatively nicely. And importantly, the material can be produced in a procedure which takes place at room temperature, which leads to very less defects and in very short time. So by that, we were able to make the material to even use them directly in such a printing machine to make some of those OFED material, which show quite good here mobility, electromobility. The model devices under clean room conditions and under argon shows a better mobility, but you have to understand that this mobility in our OFED material has been achieved in a process which is in ambient conditions. So there is air around, for example, and that needs a high stability of the material also under those conditions. It works also well to make really high molecular weight. I can show you here that we can get material by that procedure of a molecular weight up to 1 million. And the most important part is this material is very well defined and it's soluble. There is no side reactions which causes any defects or premature cross-linking. So we can have soluble material of 1 million. And we can also reduce significantly the catalyst amount. I mean, that's one problem. The catalyst has to, in conjugated polymers, should be as low as possible because it changes the properties of the material significantly, the electronic properties. So when we have such palladium catalyst chain growth polycondensation, we can get a product at room temperature in 1 hour with 10 ppm palladium. And if we use a conventional method of an AABB type monomer, we need 100 times more catalyst, and we need 30 times more time to get a similar product out of it. And our molecular weight are even much better than what we got from the other one. So I hope it shows you there is still a lot of possibilities in the synthesis to make such functional conjugated polymers. You can, of course, also still use the Stille one. We use Stille quite a bit. We liked our material by that one. We optimized it to really very high mobilities by optimizing the synthesis part as well as the structure part. So you need a certain molecular weight, and we notice that the molecular weight is really important to get good performance later on. And by that we could really make a material which is, for example, used in an oscillator and which can go into printed loudspeaker material, for example, and it works very well, shown with our partners. So the last minute shows you only that that's of course only one part. You need, for such electronic material, you need not just the semiconductor, you need also other material, dielectric material, for example. Here we contribute with hyperbranch material, for example, hyperbranch polyphenolanes, which we adjusted for cross-linking. So we have a bit cross-linking moieties in here, so triple bonds. And when you see triple bonds and are a chemist, you think always about the cycloaddition reactions, the click reaction. We did click reaction, but without the click, meaning we cannot use the copper because copper will totally destroy the electronic properties. So we used a old-time cycloaddition reaction, and it worked very well by, and it can go thermally, but it can also go through photochemically induced, and it works well. And we also did another click type of chemistry, which is the addition of thiols to this triple bond. It works also really very well. shows good performance, perfect dielectric layers, very, very stable over high frequency and a high bias range. And it works, of course, also in the OFET. And the last part, I only give you a glance. In the OLED part, you need more functional material. Here we worked on two parts. One is a material with an adapted refractive index, and the other one is the active material, which gives the fluorescent. The material with the adapted refractive index are material which contain a lot of aromatic rings and sulfur units, as shown here, and they are prepared by the addition reaction of thiols to triple bonds. And you see here, we also used a lot of naphthalene units and aromatic thiols, and there you can get a really high refractive index material. And the most important part, I have to say, it's very important that it's branched, because only when it's branched, it's soluble and can be spin casted as thin films and can be then used in such devices to actually have a very new pathway towards a low cost concept to make such devices, because up to now, most of those material are done by sputtering, so under vacuum of the different layers. But if you can do a solution casting, it's much cheaper, and you get a perfect matching of refractive index to get as much light out as possible. And the last part, also only a glimpse. That had been a development where actually was a bit lucky that we got this one. We made this polymer. We actually thought it's a nice fluorescent material which we can use, or we can cross-link. But when we looked at it a bit closer and also had our partners involved, they noticed that this material has a very specific fluorescent activity, a so-called thermally activated delayed fluorescence. And this one harvests both the triplets and the singlets from the material. So you get a much higher output of fluorescence as you can get with other material. And that was the base that we can actually do this by polymerization. So the monomer does not show this effect, but once we polymerize it to an oligomer at least, we get this beautiful, strong tuft emission. And that's also an important part and shows you the chemistry. So I think I should finish slowly. I hope I could also show you just by glimpses of some of the developments in polymer synthesis that there's a lot of potential, especially, of course, in the functional polymer system. I fully agree there had been not much new polymers, as Professor Sharma pointed out, but that is not true for the functional part. I think there are a lot of specific polymers developed lately for high-tech applications. You might not see the polymers there, but they are essential to bring the application forward. If it's in electronics, it's in sensing, it's in robotics, it's in biomedicine. In all those fields, you see now the polymers very specifically designed for the application. They are not the major components. The major component is the final device and is the application in therapy and so on. But they are fully essential to actually bring the technology forward. And therefore, I think it's a good time to thank Hermann Staudinger to provide us the base for macromolecular engineering and to give us the tools in hand that we can do as a synthetic polymer chemist. What we like to do, we make new materials and introduce and design the function for application. At that point, I thank you for your attendance, but I also have to thank all the people helping to get the results. These are some partners and students, of course, involved in the field of the polymersomes and the multi-compartment structures, and these are some students and partners involved in the field of optoelectronics. We are just a synthetic chemists, so we really rely strongly on partners which are, for example, from the physics department or from device fabrication, or especially here from the area of biophysics or also of the medical part, to be able to bring our material closer to application. thank you very much. And I hope I could, yeah, show you some nice examples of that field.
So thank you, Professor.
Thank you.
For giving such a wonderful lecture. This was our the first foundation day lecture for today. As you know, Polymer Processing Academy has completed 7 years,
Yeah.
and this is the 8th foundation day today that we are celebrating. And during this day, PPA has very particularly has the tradition of having annual foundation day program, and we have invited lectures from famous people working in the area of polymer processing and polymer science. And Professor Voigt's lecture was a wonderful lecture on functional polymer synthesis by self-assembly, and she talked about two different areas where first one was on polymer synthesis inspired by self-assembly to make nanocapsules and for synthetic biology and biochemical um, you know uh, systems materials. Then she talked about polymers designed for flexible and optoelectronics, and it was beautiful to see how biomolecular assembled circuits could do DNA engineering and lead to nanoelectronics. And these reactions were, as you said, they were carried out at room temperature and in a very short time. So these were under very benign conditions that these polymerizations were carried out, and they showed very high electron mobility. So it was wonderful to see how we can also learn from nature, and how we can play with the chemistry of the molecules which are assembling either by layer or through the polymersomes, catalyzing, which are encapsulating the enzymes, and how the synthesis is going on in the chemistry. So this is a modern polymers scientists working in the area of functional polymers through so many new routes that people have discovered and are working on. So with this, we thank you, Professor, for giving such a wonderful lecture and the insight into your work. And now we move on to the second PPA Foundation Day lecture for today, this evening. And that will be given by Professor David Hogland from US. I would like to briefly introduce him. Professor Hogland received his undergraduate and graduate chemical engineering degrees respectively from Stanford University and Princeton University. In 2005, he joined the Polymer Science and Engineering Department at the University of Massachusetts, Amherst, as assistant professor, where he has worked ever since. He is now professor and department head. He maintains a visiting appointment at the Shanghun Institute of Applied Chemistry, state key laboratory for polymer physics and chemistry in China. Hogland's research has shifted over his career, starting with polymer deformation in flow before moving to polyelectrolytes, and then to single molecule imaging. Recently, he has shifted his efforts mainly to polymers and ionic liquids, with his largest current project exploring the use of electron microscopy to perform nanoscale imaging of solvated polymers and particles. Hogland is a fellow of the American Physical Society, and he has a Sigma 11 distinguished national lecturer. His main professional society affiliation is with the Division of Polymer Physics of the American Physical Society. And although he has organized several international meetings on polyrectolytes. So we look forward to your lecture, such an interesting topic which you have chosen, Professor Hogland, and I just give the floor to you to deliver your lecture. the second Foundation Day lecture for the 8th Foundation Day of the Polymer Processing Academy that we are celebrating today. So over to Professor Hoglin. Thank you.
Thank you. I guess it's late in the evening for you and early in the morning for me. So let me set up my talk. And if it doesn't work, let me know. Give it 1 minute. And do we look good?
Yes, yes, it is looking good. We can see that.
Okay, so
okay,
I appreciate this opportunity to speak. I've never been to India, but I have high hopes that someday I'll be able to visit many of you in person. This is a little bit of an unusual talk for me. I normally don't give a perspective type of talk, but I thought this was a good opportunity to start and to present on a topic that had been in the back of my mind for quite some time. So I'm going to blend this perspective with a little bit of history of polymers and talk a little bit about polymer science and engineering as a discipline and how that discipline evolved and how that discipline is leading us to the future. But I'll start with a little bit of historical perspective since this is a special time for polymers. Polymers, of course, have been known for a long time, and the term polymer itself goes back to 200 years, so a long time. But polymers certainly weren't understood 200 years ago. And polymerization is a word that's almost as old as polymer. What's important about polymers, of course, is the structures. We just had a very nice talk about the structures that polymers can make. And so without understanding the structure, polymer science really doesn't exist. And so I don't think these old citations really are polymer science. There were some discoveries afterwards up to the period of the early 20th century, and in particular in the early 20th century, the understanding that polymers were chain molecules was beginning to be understood, and that's when Staudinger entered the field. So why is this the centennial of polymers, and why do we celebrate 100 years of polymers? And when I speak to students and now when I'm speaking to this audience, I think it's important we all know a little bit about the history of our field. And it was in 1920, so 100 years ago from this year, that Staudinger postulated that high molecular weight polymers were composed of long chain molecules that covalently connected repeat units. And so this was an important statement, but a very controversial one. And he was mostly disbelieved when he made this postulate. And it was a postulate because in 1920, he didn't have evidence for the statement that he made. He was just proposing this statement about the nature of polymers. And he was vigorously opposed by chemists of his generation, even within his own department. And I have a quote there: abandon your idea of large molecules, purify your products, they will crystallize and turn out to be low molecular weight compounds. And that was the view of the era, that polymers were in fact composed of aggregates of small molecules that created colloidal size objects in solution. And so Staudinger's view was contrary to this convention. And over the subsequent years from 1920, particularly starting in 1922, Staudinger published papers where he worked to find solid evidence for his hypothesis. The first paper was in 1922, where he hydrogenated a polymer and showed that this did not change its polymeric nature. It was believed that it was the association between unsaturated bonds that caused aggregation. And so if there were no unsaturated bonds, there would be no aggregation. But these molecules stuck together, these objects did. And that was one of the bits of evidence that he needed to establish his postulate. And I will give a little bit more background to Staudinger, but he obviously won his battle and ultimately did receive the Nobel Prize. But it's important to realize that he got the Nobel Prize for discoveries in the field of macromolecular chemistry and not for the discovery of macromolecules, as I see sometimes stated. But he really is the founder of our field, and so I think it behooves us to appreciate what he did. So this paper in 1920, 100 years ago, was in German, of course, and I don't read German, and so I found an English translation of the paper. And there's a quote here from that paper that describes what he thought, and then I took some of the images from that paper and put them on this slide. You can clearly see the structure of a polymer as a linear chain molecule, and pretty good at both polystyrene and polyisoprene. And you can see the idea of polymerization shown at the bottom. He didn't get everything right, but given the data at the time, it was quite a remarkable advance. So I'm now going to give a little bit of perspective on history of what emerged from what Staudinger did. He received the first Nobel Prize in polymers in 1953, as I said, for his contributions to macromolecular chemistry rather than the discovery of macromolecules. But there's been 6 or 8 other Nobel Prizes. The previous speaker mentioned one of them in 2000. And of course, if you take a very broad view of polymers, there are probably other Nobel Prizes that had strong polymer components. For example, the discovery of DNA. As I said, the focus of this talk will move towards a perspective on polymers as a discipline. And the first thing I kind of noticed looking at this list is that polymers seems to be considered a field that falls under the umbrella of chemistry. And some of us might be surprised. I'm not trained as a chemist, and I know many people in the audience are in processing. But that shows how polymers has grown since its advent into something broader and deeper than it was originally envisaged. But still, the field seems to be associated more with chemistry. Another factor that I see here is there's an increasing pace of Nobel Prizes. The first prize took 30 or 40 years from the discovery to the prize, and then the prizes came very infrequently. But in the last decades, polymers are becoming better recognized and more accepted as a subject of scientific inquiry. So I'll get myself into a little bit of trouble here. I think polymers did start in 1920 because prior to that time, people did not have any understanding of molecular structure. And at the core of polymer science is a relationship between this structure and properties. And certainly there were no proposals about those relationships prior to 1920. So polymer science or polymer science and engineering really did start in 1920 with Staudinger, despite most histories going further back where people were doing things totally empirically. But the acceptance of polymers didn't happen in 1920. And in 1926, there was a very famous meeting in Dusseldorf where there was a debate about what was called Staudinger's macromolecular hypothesis. Many people still in 1926 disagreed with him, but that set the stage for the eventual acceptance of polymers over the next 5 years or so. So really key developments, and this slide is focused on key developments in the history of polymer science. But that wasn't a scientific development, that was a social development as polymers were recognized. And as I go through a little bit more of the history of polymers here, it's important to note that there's a wonderful book on the origins and growth of polymers that was written by Herbert Morowitz, and it's quite readable, and it goes up to about 1960. And so I think it's a nice book, and it's in paperback, relatively inexpensive, and I recommend that anybody who considers polymer their field to actually read that book, and it discusses much of what I will present in the next slide or so. So what were the key developments? Well, this is a personal view, and I'm just going to go through the history here of the key players and the key concepts as they were introduced in time. And so obviously very early on in the polymer history, Hermann Mark became involved. Hermann Mark eventually became a little bit of a rival of Staudinger, and they had their disagreements. But Mark made many important early discoveries. For example, how polymers pack into crystals, the importance of intrinsic viscosity as an easy measurement that proves polymers are of high molecular weight and of large molecular size. And probably today where we would most commonly associate Hermann Mark's name would be the idea that polymers are flexible. In the original view of Staudinger, polymers were essentially rigid rods. So they were straight molecules. And clearly that picture causes problems in interpreting the properties of polymers. And Mark and others looked and established a flexibility. The next item on this list is probably new to most people. It's not mentioned in most polymer texts at all. But silicone polymers are enormous product in the modern world. We use them for all sorts of things. And in fact, the discovery, the polymers like polydimethylsiloxane occurred very early in the history of polymers with the first reports in 1930. And so, surprise, I put that on the list because I think those polymers play a significant role in our industry. Other developments going through this list, of course, Carruthers, very well known for developing nylon and polyester polymers. Another development that I think is not likely on many lists of key developments in the history of polymers is the development of emulsion polymerization. Emulsion polymerization was actually started to be developed before the macromolecules were accepted. And this is important because it led to the development of rubbers or elastomers at a commercial scale. And the first work there occurred in Germany, and then much of the later work occurred during World War II. And it was very important because it led to tires and lack of need for immense volume of natural rubber. As you heard in the introduction, I've worked on polyelectrolytes for much of my career. And so the idea of charged polymers and their role, particularly in biology, I think is important. The first polyelectrolyte was synthesized in 1938, and the understanding of how the presence of charge or ionic groups on the polymer backbone has on their properties evolved over an early period leading up to Jerry Manning, who's actually still active, even though he's a historical character in the field. One of the developments that's cited a lot in the history of polymers is an understanding of how chains fold in crystal, and in particular that the polymer chains go perpendicularly through lamellae. That actually was discovered in 1938, but nobody paid attention to that publication by Storks. And subsequently in 1957, Andrew Keller rediscovered this nature of the chain in the crystals and the folding of polymer chains in crystals. And this was an important development because understanding what polymer chains do in crystals is important to understanding all of the properties of semicrystalline polymers. The Flory-Huggins theory of mixing of polymers came during and after World War II. We're now moving into the period after the war, and we see Flory and others develop theory of rubber elasticity, which is something we teach every student in polymers, even undergraduate students who are new to the field. Understanding and being able to measure molecular weight is key to polymer science, and the first really reliable way to do that was light scattering. Light scattering was developed in the Brooklyn Poly under the particular lead of Bruno Zim in the late 1940s. Viscoelasticity and the mechanical behavior of polymers under stress was an important development in the 1950s associated with people like Rouse and Zim and John Ferry. And I particularly point to the development of the principle of time temperature superposition. moving forward in time, and we are getting to the end of this list, I'm not just going to rattle on forever, was the development of anionic polymerization. Anionic polymerization leads to well-defined polymers and block copolymers, and first developed by Schwark in 1956. The next item is another one I rarely see on lists of key developments in polymers, but gel permeation chromatography provided the first tool for measuring the polydispersity of polymers and easily measuring their molecular weight. Light scattering is a bit difficult. And that came out of biology, actually, and biopolymers, and that occurred around 1960. And now we're getting into the last few items, which are the understanding of rod-like and crystalline polymers, starting with Onsager and Flory again, reptation and melt dynamics associated with De Gien and Edwards in the 1970s. And then in my lifetime, I only have listed two here, and these obviously can be debated a lot, but I think the development of living radical polymerization in the early 1990s has really transformed our field by allowing very complex polymers, well-defined structure to be synthesized. And then the enormous focus on block copolymers and the morphologies and phase diagrams for them, which occurred with Thomas and Bates. So that's one person's view of the key developments in polymers. And if you disagree with me, you can send me a note and I'll probably change this list. I have thought about this for a while. Most of these discoveries didn't get the attention that you would get for a Nobel Prize, but I think if we had Nobel Prizes for polymers, all of these discoveries would get polymer Nobel Prizes. So the observation of that list of discoveries is that the field seems to be slowing in the pace of fundamental discoveries. But if you look at the Nobel Prizes, the pace of Nobel Prizes is increasing. So there's a broader recognition of polymers as an accepted part of scientific endeavor as a field. In the early years, if you read discussions by people like Staudinger and Mark, very hard to get polymers accepted as part of science. I'll relay, I won't put this in writing, I'll relay a comment that I heard on my first day as a professor, going to my office in the elevator, and there were some people in the elevator from our chemistry department. And one of them said that polymers was a cancer on the field of chemistry. And so there was a lot of opposition to polymers in the early days. And I think this hostility is gone. And that's a wonderful accomplishment for the field as a whole. If you look at those list of discoveries, you'll see that most of them early on were made by single investigators. And today, most of the discoveries are made by teams of investigators. Very often the discovery comes by combining some new technology, whether it's the discovery of AFM or electron microscopy, and applying that to some new polymers or materials. And so there is a combination of tools with materials that seems to be driving polymers forward today. And important to what I'll talk about later in my talk, many of these discoveries come from institutions that are heavily invested in polymers, meaning they have the infrastructure to really characterize polymers properly and prepare them properly. And often they have collaborating researchers at one institution, whereas in the early days, most people who were pursuing polymers did it on their own, maybe in a chemistry department or in a chemical engineering department. So I think this little bit of history lesson showed that polymer science grew out of chemistry, and the remaining part of my talk will consider where does polymer stand today. And you can see the key questions. I actually wrote this slide first when I prepared the talk. Is polymers a viable independent discipline? Are we a subfield of a bigger discipline such as materials? Or do we exist as an interdisciplinary activity that combines fields from across science and engineering? And I ask those questions because we get asked those questions nowadays all the time. And I'm going to talk a little bit about the state of polymers in the United States. As I said, when I visit India, I can learn about the state of polymers in India. But in the United States, there are only 3 or 4 academic polymer departments in the country out of the hundreds of chemistry and materials departments. And the funding that we get to do fundamental research comes from our National Science Foundation. And that funding flows from the Division of Materials Research. Rather interesting, there aren't polymer programs in the chemistry or engineering areas of the National Science Foundation, although they do fund some science in polymers. They do not have specific programs for funding polymer research. That funding comes from materials research, and that therefore has a strong impact on what an academic can do in the United States, because if you don't get funding, you can't do the research. But the largest polymer meetings in the United States are those of the American Chemical Society and the American Physical Society. The Materials Research Society, which is the major meeting in materials, is a much smaller meeting, and certainly in polymers, it's much smaller. The other interesting development relative to polymers is a discipline that I've seen a lot in the last decade, is its connection to what is called soft materials or soft matter. We had a speaker from MIT give a talk on polymers last week in our department. He refused to use the word polymers, and he referred to his materials as soft materials and said that soft materials and polymers are the same thing, which was a surprise to me. But I think part of that comes from the association between polymers and plastics, and today plastics has a really bad name in our society. And so connecting polymers and plastics is something that many people don't want to do. And so the word soft material is a way to be a little broader and a little less specific, but really to talk about polymers without the connotation of the fact that they're wasteful and hard on the environment. So with these developments, it's interesting to note that Staudinger founded the first academic polymer research center in Freiburg in 1940. So he moved outside the traditional academic boundaries to form a research center. And Mark, very soon afterwards, founded the first US academic center in 1946. So these started a long time ago, but in the United States, there's only 3 or 4 of them still in polymers. Staudinger, because of the difficulty in getting papers accepted into chemistry journals, founded the first polymer journal in 1943, and Mark founded the first polymer-focused journal in 1950 for the same reason, that the papers in polymers and the discoveries in polymers were not being well accepted into the traditional chemical journals. And interestingly, Staudinger started the first partnership between industry and academics in polymer research very on. I can't read the year here, but that's certainly a path that many departments, such as my own, have followed ever since. And that is to bring together polymer industry and academic excellence in a targeted place where there is a lot of infrastructure, essentially a polymer research center at an academic setting. So that's sort of the historical perspective that I have brought forward. And now I look forward to the future. And I looked around at the celebrations of the 100 years of polymer science that have occurred this year, and found this comment, the next 100 years of polymer science in the literature. And this comment was written by the whole set of editors and editorial advisory board. So more authors than I've ever seen on a polymer paper. But I took a quote from that paper, which is the text in the middle of this slide. And it refers to 3 of their editors and members of their advisory board about the state of polymers as a discipline. And these statements all reflect the fact that polymers is tending to become multidisciplinary, lying at the at the meeting place between different disciplines, and that polymers needs to be very careful not to lose its identity as an independent field. In the first statement, for example, Patrick refers to polymers as a fundamental discipline, and if we see the last statement, polymers needs to retain its own basis. So if polymers is dissipated and becomes an understanding of particular materials across all disciplines, we lose the strength that comes from learning the basic principles of polymers as a field. And these authors are concerned about it. And in fact, that's been my concern. And are polymers able to withstand the challenge of the next 100 years? And will there be polymer journals and polymer departments and polymer meetings in 100 years? Or will we be going to meetings of other disciplines and reading other journals? In this particular article or comment, they had identified 3 areas of significance for the future of polymers. I'm not sure I agree with them, but new synthetic methods, advanced properties and functions, and sustainability. And advanced properties and functions, of course, could cover almost everything that goes on in polymers. So it's a pretty conservative view. But the third item, sustainability, is one that we hear about every day in the polymer field today. I see there's a special session on it later at this meeting. And so the question here is, how is polymers going to attack sustainability? And so it's interesting to see how the polymers as a discipline will work towards this problem. So I quote from another literature work that occurred, I think, this last summer. This is a guidance on sustainable plastics from a meeting of luminaries in England who identified the challenges to sustainability in polymers and how the future directions that need to be attacked in order to address this problem of sustainability. And so I thought I would go through some of their conclusions and look to see how polymers as a discipline is positioned to address this new challenge. And so they have 4 points on, and these are direct quotes. I removed some of the text about toxicity and epidemiology and so on to focus on the physical sciences question. And the research challenges are enumerated, and some of the words were highlighted, not by me, but for example, in this research challenge 1 for sustainability, they highlighted the word analytical methods for microplastics and nanoplastics of different types, shapes. And that is a polymer science challenge. We develop analytical methods and we apply them to plastics and nanoplastics. So clearly a classical polymer tool needs to bear in sustainability. In research challenge 2, we need to come up with synthetic methods for making polymer structures that can be disassembled and controllably broken into smaller pieces. Wow, that's classical polymer synthetic chemistry, no different than what we've done over the last 100 years. They have 2 more challenges. The third challenge is we need to understand methods for labeling, identifying, and separating waste plastics and composites. We need to have methods for enhancing recyclability involving depolymerization of polymers that are closer to equilibrium. Again, I look at that and say, wow, that's what we do. And lastly, there is this need to understand degradation of polymers in the natural environment and understand the properties and performance of polymers, optimize the polymers and performance for specific uses. Again, that's what polymers has done for the last 100 years. So what this slide is, I took out words from that study. And you see words like rheology and mixing and phase separation, new polymers and polymerization, crystallization, plasticizers and additives. Solving this problem of sustainable polymers is exactly what our history has prepared us to do. And so the challenges ahead, in my view, are not too much different than in the past. Our basic principles are appropriate to the future. But these are going to be tough challenges, and they're probably harder than the ones we've addressed in the past. Sustainability will not be something that happens overnight. And polymers, although many comment that plastics need to be banned and removed from the environment, polymers are not going to play a lesser role in society than they do today. They just need to do whatever they do better. And so that is a challenge for polymer science. So the message here from my perspective is that maintaining polymer-oriented businesses and research centers and departments is going to be just as important in the future as in the past. If we want to look at the list of challenges at the top of the slide and all of the processes and materials involved, we need to have centers of polymer excellence that have the infrastructure and the intellectual horsepower to look at these in a combined and comprehensive way. And so, paraphrasing a quote from this earlier article on the future of polymers, polymers is not and cannot drift away from being a fundamental discipline. What are the additional fundamental challenges for polymers of the next century beyond sustainability? Because most of us are probably not going to focus in that area. And I listed a few ideas here. Some of them I've tried to explore. Some I don't even fully understand. They're so new. But for example, polymer informatics is a way to come up with new synthetic schemes for polymers using past data and using artificial intelligence to find patterns and make predictions. Polymers and active matter is a big area in the United States, and I tried very hard myself to figure out how to measure the rheology of active matter systems, and I didn't get very far, but certainly that's a challenge that has to be addressed. I threw nanoscale imaging onto this list because, as the introducer mentioned, that's what I do myself, and I think it has a future. The idea of doing microscopy of polymers in real time down to the nanoscale is emerging now, and the tools are just being developed. In the United States, probably polymers and energy would be the first topic that was brought up as a challenge for the future in polymers. And I cite that the use of polymers in batteries and fuel cells has obviously got room for further research. And the polymers in healthcare, wow, you could make a whole nother slide about the use of polymers and implants in diagnostics and drug delivery. So we have our traditional kinds of challenges, which I'd say are on this slide. Sustainability is an overwhelming challenge, but the basic science, the basic principles to attack all these problems are in our field, and we need to go forward with them. So that makes you wonder, why did I give this talk today? And so I thought I would have to justify it. And frankly, in the United States, I think those of us in academic departments and research institute are worried. The traditional departments, particularly materials, but also chemistry and chemical engineering, are advancing their polymer efforts. They see the growth in our discipline, and they're trying to pull it into their realm. And that's drawing away funds and students. Most of these departments don't have the central infrastructure to do polymer work very well. So they're groups or individual investigators. And so I'm a little concerned about that tendency. My own university is considering opening a material science and engineering department that will include polymer-oriented faculty and students. And how a materials department with polymer efforts can coexist on a campus where we have a large polymer science and engineering department seems awkward to me. And I'm a little concerned about why our administration feels the need to push on that. In the last few years, Georgia Tech lost its polymers department effectively. And just a few months ago, I'm not even sure it's formally settled, Akron, which is a huge center of academic polymer research in the United States, was demoted. It used to be a college of polymers, and now it's an informal interdisciplinary program. At the same time as we're seeing polymers a little bit sort of move into new areas, which is a good actually, because it means that polymers are relevant and important. We are also in our department doing lots of problems that are not polymeric. I, for example, study nanoparticles. I have colleagues who study surfactants. Should we do this work in a polymer department? And I've always felt comfortable about that, but it makes us wonder as a faculty, should we rename ourselves? The word is, should we change our brand from polymers? For example, it's been proposed that we should become a department of polymers and soft materials. And I'm a bit skeptical about that. In the course of doing the background for this talk, I can't help but notice in the writings of Staudinger and Mark, where we started this talk, that they wrote about the same pressures 50 years ago and 80 years ago. And as a response, they founded polymer-focused journals. They formed polymer-focused research institutes and academic efforts that brought together people who worked across the discipline of polymers so that there would be a synergy in their activities and efforts. And so I guess I feel, wow, what I'm seeing today maybe has always existed. I just didn't see it before, that polymers has always had to fight for its acceptance as a discipline. And I should just accept that and go forward. So in conclusion, I have a quote from an article from a few years ago from Ringsdorf, who was, this article was about Hermann Staudinger, but Hermann Ringsdorf seemed to be concerned in this article about the same things that I've addressed in this talk. And he concluded that polymer science has found its place as a fundamental science. Us older polymer scientists, I guess I have to consider myself one, have to yield to the creative minds of a younger generation and work towards their dreams. I mean, Hermann Staudinger had a view of polymers broadly encompassing lots of biology and other disciplines. He had a very broad view of what he was doing. And we're still on the path to his vision. And we will have new challenges and goals, but polymers should feel very comfortable that the field should feel very comfortable that they're well positioned for the next century, and that the tools that we study, the tools that we apply are the same ones that we're going to need to attack new challenges. So thank you. I hope this somewhat philosophical talk generates some additional discussions and thoughts from others. I am an engineer. I typically give hard technical talks, but for today, I've made an exception and sort of spoke my mind. So thank you for this opportunity to speak.
Professor?
Yeah.
Yeah, can you start?
Yes. Yes. Thank you so much, Professor Hoagland, for such a stimulating lecture. I think you really focused on today's topic of our Foundation Day lecture, that is 100 years of polymers and beyond. So you really talked about the history, starting from the history of polymers, so many people contributing to the polymer science and technology as it exists today after Staudinger, and what is the current status of polymer science across the world. Because polymers are being applied in so many fields, starting from energy to healthcare to safety to electronics and so on, textiles, that now the polymer, the new polymer applications has made it an umbrella under the material science department. And as you have rightly said, that polymers are now being looked as soft materials, different from plastics. And plastic applications are different, which every layman knows what a plastic is, and because it goes into so many very necessary elementary applications, and the the future, what are the challenges the polymer scientists are going to face. I think it was a great lecture, a very stimulating lecture, and you posed a very fundamental question to all the young polymer scientists who are working in this field. Thank you so much, Professor Hoagland, for giving such a philosophical lecture on the challenges of polymer science in the years to come. With this, I move on to the next. So this was our Foundation Day lecture 2. And after that, I would request Professor Anup Ghosh to take over. He will also announce, he will give a propose a vote of thanks and also announce the PPA Fellowship Awards. So now on to Professor Anup Ghosh.
Thank you, Professor Mangla. Indeed, it is really the endeavor that we had under Polymer Processing Academy program. Every year, we actually try to organize this the Foundation Day program for our Polymer Processing Academy. And this year, the emphasis was this 100 years of polymers. And I think with the presence of Professor M.M. Sharma, the eminent person in this program, and with the 2 keynote speakers who have presented for our Foundation Day program, the 2 very important aspects from the 2 angles it has come forward. The way the new functional materials, the developments that are happening, which is Professor Foyt presented from the very beginning to bring it out, and polymer is changing to a new functional materials and so many new applications. So there is no stopping about it. But at the same time, Professor Hoagland put it together, the other perspective, the challenges, and whether we have to think. We have to think when you're moving forward. You really put it to us in front of us. And I think young scientists, young students, researchers who are there, many of them are attending today's program. And they must be taking cue from here that how to think and think about the new areas and which are the different areas to work. And I think more challenges lead us to move forward to do newer ways to move on. Okay, so I think it was an excellent program. Okay, and we are very happy to have all eminent personalities to be present here on our Foundation Day program. We generally look for some of the areas, and we are extremely satisfied with our theme that has been taken for our Foundation Day program today. Traditionally, what we have is we have our eminent personalities invited on this day to preside over the function and for the Foundation Day lecture. And as a part of our Polymer Processing Academy program, we generally very happy to honor our chairperson and the key speakers of the Foundation Day, what we call as our Polymer Processing Fellowship. And by this way, we actually reach out to them to be part of us in our Polymer Processing Academy program to enrich us with your experience, knowledge, and involvement. Okay, and with this, I also now request Professor Mishra to take over and hand over the Honorary Fellowship of Polymer Processing Academy. We are very happy to have with us Professor M.M. Sharma, the Padma Vibhushan awardee, is a FNA FRS, and is a distinguished professor of eminence, a former director of ICT, which used to be known as UDCT, to be with us. And may I request Professor Mishra, Ashok Mishra, to confer this certificate, because you have to do everything online in this very special situation. Generally, we do it in presence of everybody and by physical presence. Professor Mishra, please.
So it's a pleasure to confer the honorary fellowship of the Polymer Processing Academy to Professor M.M. Sharma, whom I have held in such high esteem throughout my professional career, and also to have come and inaugurated the function today. Professor Sharma has been a friend of Polymer Processing Academy. I remember he came to other functions of the Academy earlier. So virtually, I confer on behalf of the PPA, confer the honorary fellowship of PPA to Professor Sharma. We'll send you the certificate by mail. Yeah, you have to unmute, Professor Sharma. You have to unmute.
It's a pleasant surprise to me. Thank you very much. I just wanted, if you permit me, 2-3 comments I wanted to make. Can I?
Yes, yes, of course.
You know, the talk given by Professor Brigade was fantastic. I just wanted to know from her that with the directed evolution work of Francis Arnold, where one is projecting that we will be able to do many things beyond nature, synthesizing, through biocatalysis and all. And with the kind of work she has reported, there would be some kind of an extraordinary synergy from what she presented and the Francis Arnold's work on directed evolution of enzymes. And somehow there was no mention of interfacial polycondensation. Lastly, I wanted to make a comment that there are polymers which are used as a medicine. For example, phosphorus load in the dialysis patients, the so-called drug is polyalylamine cross-linked with epichlorohydrate. And with the potassium load, it is polystyrene sulfonic acid. They are called drugs, but they are polymers. It's interesting that people don't know that polymers are being used as drugs which you swallow.
Yes.
It's very interesting. Thank you. Sorry, I thought it was not appropriate, but I thought I'll seize this opportunity to make this.
Thank you. I hope we get the chance to discuss this in more detail, because we can a lot of things to discuss. I see a big future for the polymers also in developing closer to nature and to take really functions of the nature. I still have to admit we do small steps towards. Nature is much better than we are and can cope with much more complex information processing as polymers so far can do. But we are making progress, I can say. And you're fully right. For example, we really also work on polymeric therapeutics, where the polymer structure by itself is a drug. So not a drug carrier, but the drug by itself. Especially there are some fields like our glycopolymers, which we work with. So yes, there is a big future, and I hope for it, for the functional polymers, of course. And I think we get closer to the complexity of nature and build them also with polymers. But that means also a very complex synthesis, I have to admit. So it will be not on large scale. Thank you. Thank you.
I'll unmute myself.
Yeah, thank you.
Thank you, Professor Sharma. And in fact, I like to show you, this is our logo and the certificate. I mean, there's an award. It is our honor that you have accepted that fellowship. And this we generally like to give. We will make this, see that it reaches you. Let's see in what situation and what time we can do that. Next, we are very happy to confer our honorary fellowship to today's first Foundation Day speaker, Professor Brigitte Foyt. And may I request Professor Ashok Mishra to take over and confer the fellowship.
It's absolutely a pleasure to confer this award of the Fellowship of Polymer Processing Academy. Now you're part of us, so you have to give more talks to our functions and so on. But it was excellent that you came and gave this talk. Thank you so much. And the beauty of it is, as I was mentioning, sorry, the electricity went here, is that in this sort of a situation, we have international speakers. We don't have to go and receive them at the airport. We don't have to worry about hotel accommodation. It's all virtual. It's fantastic. It's for the first time we've done it, and I think we have a good start today.
Thank you very much. It's an honor for me to take it, and it's a pleasure, of course, also. I have to admit, I'm not really in the processing, but I feel without the materials you synthesize, you cannot process anything. So I think it's still important, and it really fits together because the synthesis and the structure build defines very much the processing. So I feel also well in that field. That's fine. Thank you very much.
Most welcome.
Thank you, Professor Voigt. And I like to say that actually on these days, physically, we were supposed to have the conference in Bangalore. Well, under the aegis of Polymer Processing Academy, along with the Polymer Processing Society Regional Conference. But because of this pandemic situation, we had to postpone. It has been postponed, it has not been cancelled. And we look forward to the opportunities when we'll do this conference to have your presence physically with us and with another key lectures as our Polymer Processing Academy fellow. And we'll be waiting for that. We'd love to have you with us. And a lot of our colleagues from many different institutions, IITs, are actually already collaborating with you. And from my visit, I know that when I visited you and I was in Dresden.
Yeah,
and
so yes,
if
I
you
have
remember,
quite strong contacts, I admit, but a bit more to the north, like Kharagpur is our main part, and also Delhi. But so I had been in India quite some time. So, and I look forward to come back.
Sure.
Okay.
We look forward to your visit. Okay.
Thank you.
Okay. Our next fellowship award to be conferred to Professor David Hoagland. And may I now request Professor Ashok Mishra to honor him.
So again, it's a pleasure to confer the honorary fellowship of the Polymer Processing Academy to my very good friend from University of Massachusetts, David Hoagland. As some of you may know that I did my PhD at the University of Massachusetts. So I have a very strong bonding with them. And as David mentioned, the department has changed quite a bit from the time I was there, from hardcore polymers to soft matter, as he put it. And I'm an adjunct faculty there. So thanks so much, David, for accepting to give this talk. And I really enjoyed it. And now you have a new talk, which you can present at many places. I would, of course, like to have a copy of it. It's fascinating how things are changing. Thanks so much, David, for being
Well,
there.
thank you. I was a little scared to give this talk today. As I said, I'm an engineer, and I don't normally give fuzzy talks. I like to put plots and equations onto the slides. But I had something on my chest, and when you guys gave me an opportunity to talk about the future of polymer science, I thought it was a wonderful opportunity to get this off my chest and hopefully to inspire some other people to think about our field.
Thanks so much.
Thank you, Professor Hoagland. I must thank you that you got up so early. Maybe not so early, but we knew that you had to take that time frame that you have to be with us. And we were wondering, and I can see that. And also, I know that you were not physically keeping well a few weeks back, but still you accepted our offer and specially request by Professor Mishra to be with us. It is excellent. It was a good combination because there was a chemistry, there's an engineering, and you're bringing together, and you gave us a little bit thought-provoking points that we must think about it. Also, you said that you have not visited India, so we look forward to that. We welcome your visit. We look forward to your visit. As I said to Professor Voigt also, that we'll have our the bigger conference coming, or even earlier. If you visit us, we will be happy to have you with us in any of the institution and connecting with all members of the Polymer Processing Academy. And I'll say that this is the beginning of our interactions with you.
Thank you for all the kind words.
Yeah. And before we close, I'll again like to thank Professor Sharma to set the ball rolling. He works in so many areas of chemical engineering, and as you can see, in polymers, he knew so much more than many polymer scientists would know. So he was the right person to chair the meeting today and inaugurate the 4-day conference, a 4-day event Today is the foundation day and the 3-day conference to follow. And thanks again, David and Professor Brigid.
I also, on behalf of Polymer Processing Academy, extend my vote of thanks to Professor Sharma, all keynote speakers, the distinguished guests who are here, the members of Polymer Processing Academy, the many faculty, many research scholars and students are attending this. I have two statistics that we have gone to our 8th Foundation Day program, which shows that we are moving from the inception of Polymer Processing Academy. Also, for these, today is a Foundation Day program and followed by 3-day our international wave conference, you can say that. For that, I know that there are 250 registration have been done. Okay, so quite a few of them attended today, and they will be attending with based on the themes of the conference on day 1, day 2, day 3. I must say that we made a very token registration fee to see the seriousness, and even with that, more than 250 participants have registered before the conference, and we are very happy about it in the shortest possible time. Yes, we are very, very thankful to Professor Sharma. We are highly honored because this was 100 years of polymers, and we could not think of anybody other than you. And I told Professor Mishra that can you connect Professor Sharma to see that
my pleasure, my pleasure, and I enjoyed.
And you spontaneously accepted our invitation. It was so nice, and we always learn.
Ashok will tell you that I agreed right away.
I know, spontaneously, and you always encourage us, inspire us with this. And also big thank to Professor Foyt. I already mentioned that journey you have shown, how to move, how you are moving, how we should be moving, how the research areas are moving. So we have a very high sense of appreciation on behalf of Polymer Processing Academy for your kind presence and the presentation that you have given. We are very grateful to Professor Hoagland to come forward, and then the presentation that you have given on the polymer as a multidisciplinary field. And actually, when you said, I realized that what is that past, present, and future, which your perspective that you are bringing in. That was really, really very good. When you said that there is some key developments that how the polymer should move in next 100 years, that I started thinking, especially we all think about sustainability quite a bit nowadays. Yeah. And you really address that point also. Okay, we are very, very thankful to both the speakers, and you really gave us some food for thoughts that how we should move in. I would like to thank Professor Mishra, who is leading us from front. I must say that. Okay, he actually, we built up Polymer Processing Academy under his presidency. He always leading us. He is always supporting us. He's also pushing us that we have to do big program. We have to do program of this kind, and how to take, and he takes all the details, and he was attending almost all of the organizing committee meetings, even due to his busy schedule. So we are very, very thankful to him. And also we are very thankful to IIT ACB, Alumni Centre. And we are very thankful to Sri Ashok Kamath, Secretary of IIT ACB, for being with us, providing all the supports, and also the support. He has a perfect logistic support he has given and guidance in order to host this. So this program is being hosted from Polymer Processing Academy with all the support that we have got from IIT ACB. And they have provided, and I extend my thanks to Ms. Sushmita to make all arrangements and for enormous cooperation that they had provided with us, and that will continue for next 3 days. Okay, the very, very professional way she has given, and all that. I have to thank so many of my colleagues. They are part of the Polymer Processing Academy. I cannot name all of them. I do not want to take much of the time, but Professor Arup Bhattacharya was the key person in organizing this conference. Professor Surya Sharati Bose. These are the very young polymer scientists, engineers coming up, and they are taking full responsibility of this program. Professor Nikhil Singha for the whole promotion of the conference, along with all of us are there, but they were taking key roles, and that's why this program has been all put in place. I like to thank all the people who are attending the conference also. Okay. From many different places, we are not being able to see the participants. That is the problem. Physically, we cannot see everybody's face here, but you may be attending from many parts of India. Maybe some, I learned that there are some registration outside India, those who are in the different time zones, and we are very thankful to you. We encourage you to be there for the next 3 days of the conference. And I hope you will get a lot of information and learn from this conference. So once again, I thank everybody and for being present in this evening. I must say it was a great pleasure. We really enjoyed the program. Thank you very much.
Yeah, just to remind all the participants, of course, Arup may do that from tomorrow onwards, the meeting will start at 2:30 p.m.
Right.
So login is 2:30 p.m. That's all. And Arup, you want to say something?
Yeah. So once again, thank you so much for this nice program, especially Professor Sharma, Professor Foyt, and Professor Hoagland. And it went very smoothly. Professor Mangala Joshi did a wonderful job of coordinating this entire program. And tomorrow, 2:30, we are meeting again. So the link will open 30 minutes prior to the program. So, and the speakers are informed accordingly, so they can check their network and stuff. And we hope to see you more participants from tomorrow onwards. I could see today 146 and plus 25 YouTube viewers, which is not bad. But as Professor Ghosh mentioned, that we already have around 250 registrants, participants who have already registered. So tomorrow would be the session on polymer nanocomposites, products and processes of nanocomposites. And there will be 4 keynote lectures and the discussion. Thank you so much.